All right, so welcome back. Today I want to talk a little bit about the gas laws, at least the first couple of them. There are actually several, and we'll be working on them today and in lab a little bit in the next couple classes. And they all work together to talk about gases in terms of like volume and temperature and pressure and the number of moles and other variables like that, depending on how you set them up. And this actually shows up in a lot of different parts of science, not just chemistry. It shows up in physics, it shows up in calculus, it shows up kind of everywhere. And this is probably the first time you've seen them kind of in depth. The gas laws end up being pretty straightforward because you know algebra, and they end up just being algebra problems. The reason why we do them in chemistry is I can do some labs with you that are rather interesting examples of these gas laws, and I think a really good segue, really good transition from what we've been doing, which is basically quantitatively talking about reactions, and transitioning into physics, which is quantitatively talking about a world which is a little more messy. Gas laws behave really well if I want them to, but I can also just as easily set up a lab that doesn't show anything at all. It's a bit tricky. You might notice in the background of my presentation here, I've got some hot air balloons floating around. And obviously hot air balloons, we know how they work. I mean, they warm up the envelope. The air inside is warmer. Warm air rises because it's less dense. Eventually it hits some level. Blah, 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 blah. Well, that's gas law stuff. And there's actually more going on than just that. And I want to talk about predicting the behavior of gases across a wide range of changed variables. And I don't know. I don't think it's too hard, but it's relatively interesting stuff. Our objectives today are first to get you ready for your lab next. You're going to see some demonstrations of these things, and when I have them happening, I want you to understand why those demonstrations happen, because they can be very confusing too. I want you to learn the basics of Boyles and Charles law, and see how they relate to something you've learned in math, which is direct and inverse proportionality. Two pretty easy concepts. And then I want to get you ready for this in terms of like a class evaluation, which we'll do by a worksheet, which you'll get here in a moment. Now, I want to talk first about Boyles Law. Boyles Law is something that came from a long time ago, before the United States. So this is something we've actually known about as a species for a very long time. And Boyles Law is about pressure and volume. It makes perfect sense. They're inversely proportional. I'll talk about that for a moment. Basically, as you press a gas down, the pressure goes up. As you give the gas more space, the pressure goes down. They're going to be opposites. Now, one thing that is nice is this is a proportion. And so the units don't actually matter because they're going to cancel each other out. So as long as you're consistent and the same units are on both sides of the equation, you're going to get the right number. And that is very nice and very useful and not very common in the gas law world. So let's explain proportionality really fast. You need to get a tool to help you do that. Yes, this should work nicely. So I have a triple beam balance here, which is an old tool before we had digital scales. And what I'm going to do is talk about inverse proportionality for just a moment. When I press down over here, you'll see this arm actually rises. They do the opposite, right? If this thing goes down, this thing goes up. If I'm looking over here and it's up, and I push it down, this thing must rise on this side by a proportional amount. This is inversely proportional because it's doing the opposite thing. If one thing's going up and one thing's going down, they're obviously opposites, in which we call scientifically, mathematically, inverses. Now, the reason why I care this is inversely proportional is it makes sense. If I have a volume, let's say, I don't know, 100 milliliters in this flask or whatever, and I compress it down, if I don't let the air fill it anymore, the same number of molecules are in there, but I'm squeezing them down, so the pressure has to rise, right? The number of molecules per area is rising. In the same breath, if I let it go into the room, well, the pressure from that gas is going to be lower. And Dalton here is the first person to think about that. And by Dalton, I definitely mean Robert Boyle. I don't know why I said Dalton. He's a different gas law. My apologies. So let's bring it back and talk a little bit more about Boyle's law. This, by the way, is Boyle. Pretty fly guy. Boyle had this experiment here. And actually, it's an experiment you could easily carry out and do better than he did. But when you think about this being before the United States, before the French Revolution, before kind of the Enlightenment era, it's actually pretty cool to see. And it just involves some pistons together. And he was able to prove unequivocally that these two things were opposites. If I graph Boyle's law, you'll see it is not a straight line. It is some kind of an exponential decay. The nice thing is there's no logs or anything. It's just P1, V1, P2, V2. Okay, pressure and volume before, the ones here before, equal pressure and volume after. It's pretty easy. And take note, as long as the P's are in the same units, like atmospheres and atmospheres, torrs and torrs, PSI and PSI, I don't care. As long as they're in the same units, it's going to work. Same thing with the volumes. They can be milliliters, centimeters cubic. They could be in liters. They could be in whatever. As long as it's the same unit on both sides, this is going to work out beautifully. And you can tell this is inversely proportional, by the way, because you have multiplication of the same variables across. So do enough math and you'll say, oh yeah, look at that. It's inversely proportional. Whatever. As I said, what's really going on here is you're just decreasing the area and keeping the number of atoms constant. So realistically, what you're looking at here is, and let's see, if I actually think I have a graph up here. Yeah, I could have different things. So if I start off at 10 liters and an atmosphere, so I just have 10 liters of atmospheric air here, you'll note the temperature in all three of these situations doesn't change, and it can't change because there's no T in the formula. It's what we call isothermal, whatever. Now, I take that 1 times that 10, I set it equal to X, and you'll note that I can get a constant. And that constant actually never changes. What changes is just the volume and the pressure to keep it equal. This line here represents the point where those things are equal, that graph, that trace. And so mathematically, this is pretty easy. So let's look at it. I've got a diver under the ocean, and apparently she blows 3/4 of a liter of air 10 meters under the water. It rises to the surface. It rises from a higher pressure to lower pressure because, of course, the pressure underneath the water is greater because there's more water pressing on you. And I want to know how big that bubble gets from what it started from. And I'm going to assume it's isothermal, which is actually a terrible assumption in real life, but it's going to work for this problem. So let's work this problem together. Here in a moment, you'll see a new answer. There we go. So, 3/4 liter, 2.25 atmospheres, and X liters at 1 atmosphere, give or take. Now, mathematically, remember, Boyles Law is going to be something along the lines of P1 V1 equals, let's see, we got P2 V2, basically our before situation and our after situation. Now, our before situation, the heavier pressure and the smaller volume were linked. How do I know that? Because I know the pressure must be higher underneath the water. And if I didn't know that, it would be clear by somehow the question is written. So I'm going to take those two variables that are in the same spot and keep them together. So let's see, 0.75 times, let's see, my liters, 2.25 pressure, neat, equals, let's see, 1.03, and I'm looking for a volume, so I'm going to represent that with X. I can use my handy-dandy calculator here. And let's see. I have 0.75 times 2.25, 1.69 equals 1.03x. So I can take that number and divide it out by 1.03. So you can see the bubble more than doubles in volume, even though the pressure, well, basically halved a little bit more. And that makes sense. As the pressure went down, the bubble got bigger, which you've probably experienced in real life. So I don't want to hang on too much. The big thing I want you to see right now is that this equation is actually really easy as long as you're careful to keep, like, this was in liters, so this has to be in liters. This was in atmosphere, so this has to be in atmospheres. It's really important you include your labels, you include your units. Otherwise, you're going to miss some points for things that you really shouldn't miss points for. All right, and so we're back. I want to talk about Jacques Charles. Now, Jacques Charles, obviously French, is from about 100 years later, if you notice. He's a bit later. And he actually observed something kind of different. As temperature increases, the volume of a gas also increases. That is, when one thing goes up, the other thing goes up, which is the exact opposite of what we just talked about. So this is obviously some kind of a different proportion. Now, mathematically, I can write it as either of these things. V1T2, you'll notice how the 1 and the 2 are together, but make sure it's the different kind of proportion. Or the ratio V1 over T1 equals V2 over T2. This is the one I will generally give you on a test or anything where I'm providing the format. but it honestly doesn't matter. One thing to notice is I will require you to put the temperature in Kelvin for these problems. And the reason why I'm going to require you to put temperature in Kelvin is I will need it to be in Kelvin later on in more complicated things, and it's good practice to start. The other reason I want it to be in Kelvin is it gets rid of those pesky negatives, which are actually really inconvenient here. Now, before we go all the way through this into an example, I do want to talk about Jacques Charles for a bit because he's a really interesting figure in history. For one, Jacques Charles isn't actually the person who came up with this formula. That guy was named Gay-Lussac. Gay-Lussac gave Charles credit, though, because Charles was the one who derived it. He just never published his work. Now, Charles isn't known for his work on gas laws. Charles is known for his work on a balloon. Well, several balloons. He was the first person to use hydrogen to lift balloons, and he did it in France in like 1760 or so. And he launched the first balloon unmanned, and the second time, he tied a thing on and went with a friend up to like 1,500 feet and then crashed to the French countryside, which had to be one of the most confusing things possible because obviously no one knew there was going to be this balloon falling out of the sky at the time. That being said, his work on early human flight and ballooning and these kinds of things, way more known in reality at the time than his kind of obscure work on temperature and gas. And it's particularly ironic because this isn't a hot air balloon. It's actually a gas balloon. The hot air balloon, the I don't know how to pronounce them.
Montgolfier.
Ah, yes, okay. So the Montgolfier brothers. And the Montgolfier brothers, they're the ones who actually invented the hot air balloon. So it's kind of ironic because here we are with Charles, who came up with the temperature pressure relation, which should dictate how, at least in part, a hot air balloon works, and is actually someone who's not doing it. The
Montgolfier
brothers who actually invented it. Kind of backwards. And he works in this density-based thing with using hydrogen. Ironic. Now, it doesn't really matter. You have to imagine that these things were incredibly confusing at the time. What I want you to see is Charles' law actually is directly proportional. It's logical. So one thing goes up, the other thing goes up. And that means I don't have that curvy line anymore. I just have a straight y equals mx function, which is wonderful and easy to work with mathematically. Again, temperatures in Kelvin. Everything else can be whatever unit you want as long as it's consistent. So 33 liters, 300 K. What volume will you have at 235 K? Well, as long as the pressure is constant, which isn't actually that bad of an assumption. This is if you have a stretchy container, like, I don't know, a balloon, it's going to work well. So let's go back to the board here and let's see how we would do this problem. All right, so it says 33 liters at 300 K, and I want to know what volume that occupies at 235 K. So if you remember, Charles' law is a little different. If you don't remember it, it's like V1T2 equals V2T1. Or you can choose, there's a V1 over T2 and etc. But this is the one I want to use today because it makes sense to me. All right, so I need my first volume. Ooh, that's unfortunate. All right, so I need my first volume and my second temperature. So you notice, like, these things are actually going to get split up. They're going to go on opposite sides of the equation, which can throw students off for a moment. So 33 times 235 is equal to whatever I'm looking for times my final temperature. So I've got 300x equals, let's see, 33 times 235 is 7755. Okay, so x here is equal to 25.85 liters, which of course makes sense because it got colder, and as things get colder, they shrink, at least in the gas world. And so this is going to work. Now again, note, I am putting a unit on. By far the common mistake on these things, at least early on, is people forget their units. Okay, back to the table. All right, eventually we're going to talk about how to choose equations, but for now, all I need you to know is this summary slide. And I'll put this up at the top of the page should you want to use it, but Boyles and Charles' law can be summarized this way. Now what's going to happen is you should have a worksheet from your sub, And I want you to work on that. I'm going to collect it in lab, so it's due in lab as is labeled on the top of it in big words. And we'll see some of this in real life. Until then, I hope you have a great day. I look forward to see you in lab, and good luck.